so that the data that is produced is not discarded or removed. The same thing for the consumer. Okay, if let's say it's lower, if you see the buffer will get filled up. If the consumer is faster than the producer, then this buffer will be cleared very quickly. Right? So this buffer is to allow the producers to post whatever data to this consumer without needing to wait for the consumer to finish the job. Okay? But then of course, because this producer and consumer is sharing this buffer, this is shared resources. Shared resources. And it is at least one. Okay, there are two here. And you can have multiple producers as well. You might have the S at the back there because you might have multiple producers. And you might have multiple consumers. Or you can have multiple producers, one consumer. It can be something like that. Or a single producer but multiple consumers. So there are a variety of similar problems. But basically, it boils down to the same problem. We have at least two players here, two actors, and you have shared resources. And that means you will potentially cause race condition. Okay? So we have buffer here is to solve the problem, but sharing resources to get race condition. So how do we protect that? Okay, we protect it by using what we have learned before, mutex and all that. Let's look at the problem one by one first. First thing is, producer, when you produce, you cannot produce infinitely because the buffer is of fixed size, finite, okay? And it's of fixed size. So if let's say the buffer is 8, that means we have to block the producer if it is too fast. That means it produces more than 8, and the consumer has no time to retrieve any of the data from the buffer, and it gets filled up. So sometimes we have to block. Okay? And of course, if you want it to be more smoother, your buffer should be up bigger. Maybe you can increase it to 1024, maybe. Right? But let's choose a small number so that it's easier for us to discuss. Okay, let's choose 8. Right, so we have a problem here. The problem is, if the producer is faster, we need to block. Okay, if 8 is filled up already, you need to block. If of course it's less than 8, we cannot block the producers. Okay, so this is from 0 to 8. Right, so for producer, we can write down here. 0 to 8, no block. But bigger than 8, block. Okay, this is normal. From 0 to 8, so I should say 7, because 0 is part of the number. So 8 elements inside, sorry, 8 slots inside. Right? So anything that is bigger than 8, we block. That means if you don't have enough slot, then how about this? This one 7 down to 0. Yes, this is normal. But if it is 0, I should say down to 1. Because when it is 0, it is already blocked. So if 0, then you cannot get less than 0. Because you either have data or it is empty. This 0 means empty. It will get blocked. So somehow we need to be able to synchronize this, meaning that if the producer is fast, it's fine. If, as long as the buffer is there, the number of slots is enough for the producer to put in the data. But if there is not enough, then we have to block this producer. So we need a mechanism to be able to block when it fulfilled, that means it filled up all this buffer. But if it is not filled, then it should run as normal, that means unblocked. Okay? The same thing for the consumer. If the data is available, Okay, then we can retrieve. Every time you retrieve, the data will be less and less. That's why it's 7 down to 1 in this direction. Because consumer is always taking out the data, right? So the number keep on decreasing. It will be normal, that means it will be unblocked state if the number is within this range. But if it is 0, then you have to block because you cannot take something from that one, right? Because you are waiting for the data to come first before you are able to proceed. You have to block it. If you don't block, then you proceed to process nothing, which is going to be a problem, right? You cannot process no data, you have to process data. So in order to block the consumer from proceeding to process the data which is not there, you have to block it. So we block if there's no data inside it. So how do we solve this problem? We solve this problem by using counting semaphore. Okay? So counting semaphore here means the semaphore is bigger than, I mean the counter is bigger than 1. Counting semaphore, so it's bigger than 0. Right? And counting semaphore because you have to count. That means if you look at this problem here, you are actually counting, right? For example, 0 to 7, you're actually counting. If it's bigger than 7, you block. So basically, counting semaphore is doing the same thing. It counts until you reach the maximum that is specified, then they get blocked. Okay? The same thing here. We can create a counting semaphore to do the reverse as well. That means 7 back to 1. Okay? If it is 0, then we block. Okay? So how do we solve the problem for the producer? The producer, maybe we call it full. Okay, let's call it semaphore. Okay, and we call it full. Is this a variable name? And the initial value is, the maximum value is 8 because we have 8 elements inside there. And we start with 0. Okay, so this is the maximum counter that you can reach. That means if it's bigger than that, then it will block. And this is the initial value. Why initial value is 0 for the producers? Because you have nothing there. Okay, you don't have the slot. The number of slot here is free, which is free is 0. Okay, so it starts at 0. So this is for the producer. How about for the consumer? The consumer also we have the same. We call it semaphore empty. Yeah, I just give a name here because it's easier for us to understand what we're dealing with. That's why I give it this name. You can give a name, other name that is relevant to you. Okay, here also the same thing. Oh, sorry, I shouldn't start with it. I should start with it. Okay. 8 here means I have 8 elements inside there. Okay, I start with 8 because I have still 8 resources for the producer. Okay, so this 8 here is available resources. Okay, this one is the maximum resources. Okay, why is it 8? Because I have 8 more for the producer to put in. Okay? Okay, now the empty, I have maximum resources, which is 8 as well. This is maximum resources. But then my available resources is 0. Why? Okay, resources is 0 because I don't have data. The consumer receive the data, right? But initially when you start, it's empty, isn't it? So empty is denoted by this 0 because it's not available. Okay? If you want to remember easily, you think in a logical way. When the consumer comes, right? When you try to consume this, but if it is less than 0, you'll get blocked. Okay? So, but because it starts from 0, right? So you try to get one resource, but the resource is not there because it starts from 0. So you get blocked at the beginning, which is logical because initially this buffer is empty. The producer does not produce anything, so it's empty. When the consumer comes, when you try to grab it, there's no data there, so it should get blocked. That's why you start with 0. Okay, how about the producer? Why do we start with available resources is 8? The reason is because when the producer comes, if it is 0, then when you try to acquire it, there's none. Then you get blocked. It's wrong. But you have 8 more. You have 8 empty slots. You can put the data inside there. Okay? So you cannot block the producer. You must block the consumer, but you cannot block the producer. Right? And 8 here means you got 8 slots. Slots that is free for the producer to do it. Okay? Okay, so when the producer comes in, you see 8, and when you acquire the vertex, like semaphore, it will not be blocked. You will allow to enter into the critical region, and you start to put the data inside. Okay? So how does it do it? It does it by doing a dump. So that's called pull. And you do a dump, or you can okay, then there's a different name. So you can use down, you can use wait, you can use acquire. Okay, so this term is commonly used for semaphore, but the original one is actually called down, because when you do counting, right, down means you count down. Okay, this is the original word, but a lot of people don't like this name because it's ambiguous. People like to use a different name like acquire and wait because it's more relevant to the problem that they're solving. Okay, so that is for the semaphore. Down, wait, and acquire. The opposite of it is up. I should write it down there. Up, the opposite of it is up, signal, and release. Okay? If we use this terminology, there is down and up. That means the opposite one another. If we use this terminology, there is wait and signal. Okay, wait basically count down. Signal, that means it will increase. Okay, so up and down. Like that. The same thing, acquire, you are doing a down, release, you are doing up. Okay? So this is just a terminology that you will see later on in some of the exercises, because different people who design it, they prefer different kind of name. Okay? So this is the original one, these are new terms that we use. So let's call it up and down, because it's much easier to understand using if we are talking about counting semaphore, right? So let's do a down here. And what do you do? You call this method. Method is by this object. This object is semaphore. Maximum resources is specified as 8. Available resources at the beginning is 8. When we do a down, when you start with 8, when you do a down, it becomes 7. Okay? Now you have 7 slots that is free. You use 1, and of course you have to put the data inside there. So let's put it. Let's assume that this buffer is also an object. So we do it this buffer add, and this is the data that we add. The producer produced data, right? So we add the data into the buffer. Okay. Okay. How about this side here? This side here, we do it the same thing, but this time we don't look at the field, we look at the empty. Okay. Maybe I'll close this capillary. This one. Maybe I shouldn't draw there. I should draw up. Yeah. good connection. Structures. I don't have enough space there. Go ahead. Okay. So let me draw that in here. So I got the buffer. Okay, so this is going to be our buffer. We got producer, consumer, right? Where the data goes this way, in one direction only. Okay? So on the producer side, I use counting some of those, sorry, Code full, you can give it any name, okay? Code 8. Okay? And then I do a full down. Okay? And then buffer of that data. That's all. Okay? Okay, on the consumer side, there will be semaphore as well. And here is empty. And I start with maximum is 0. Maximum is 8, but I start with 0. Okay? And here, when I try to consume it, I will do something like this. I do empty and then dot up. Oh, sorry. This should be down as well. Okay. Okay, initially, because it's 0, so when I do a down, surely you get 1. Okay, if let's say the producer didn't come in and then put the data, then the consumer, when it comes in first, when it does a down, it will be blocked first. Okay? Let's say, for example, when it does a down and it's not blocked, that means there's data there. Okay? Let's say, for example, some producer comes in, we manage to put one data there. Okay? So the buffer is not empty, right? So it's not data. So when I do empty down, I got one there, and therefore I will not get blocked. And the consumer will get passed through, and then we continue to get the data. So buffer get. Let's put it into this placeholder. Let's call it data as well. As a variable. Buffer get. Okay. Now I want to leave some space there, but I might just leave it like that. Okay, so if I succeeded in doing it down, I never get blocked, or maybe I get blocked initially, but somehow the producer put the data inside there, so it will wake me up, and then I'll proceed on to get the data, put aside the data, and then process it. Okay, let's say for example here I process the data.
So the down checks the buffer if there's anything inside.
The down is just dealing with the counting semaphore only. If it is 0, then you block. Okay, so the rule, sorry, I forgot to tell you that. Counting semaphore is this. If you do a down, and once you reach 0, you get blocked. Okay?
So the down checks whether the semaphore is 0.
Yes. You check the semaphore is 0. If 0, you get blocked. If not 0, then you reduce by 1 and let it pass. Understand? So, counting semaphore, it works like this. It has a number inside there, maximum number, and then the initial value. If the initial value is 8, if I do it down, it becomes 7 because it reduced by 1. But because it's positive number, it's not 0, so you let the thread that call the function to pass immediately. You will not get blocked. Okay, it continue on. Now when it gets down to 0, okay, now it's 0 again, and I call a down on that 0, then it will get blocked. Okay, when will it unblock? Somebody else is going to unblock. Another thread is going to unblock it. I'll explain to you how to get unblocked. When somebody do an up, then it become from 0, you go back to 1. Okay, so when you go back to 1, this will be unlocked, the one that you get blocked just now, it will be unlocked. And you let it pass, and this one will be 0 again, because it's taken by this thread that is being down. Understand? Okay? Anybody who get past will do a down, and definitely it will go back to a smaller number. In this case, when you go up to 1, and the unblocked thread manage to get hold of it, then it will go down to 0 again. So whoever comes later on will get blocked. Okay? So counting semaphore is only allowing that many of resources to be used. Okay? If let's say you got 8, it allows only 8 threads to enter. Right? If I put 2 here, only 2 threads can enter into the critical region. Okay? The rest have to wait. Okay? So that is a counting semaphore. So why do we do that? Because of the buffer size. Okay? It's finite, and then we have to protect each one of these slots there. If let's say it's already filled, you cannot allow any producer to come in, because if you come in, there's no place to put. Where the data is going to be stored, cannot be stored. Right now, you can produce it, but I have to throw it away because you don't have enough stock there. So those who manage to come in surely will have a place inside the slot, right? And you get blocked if it is full. Okay, so this data will be processed eventually. And okay, so that is what happened. So this one is kind of symmetry here. The producer produces and add the data into the buffer. And for the consumer, he will do a down just to make sure that the data is there. If it is blocked, that means the data is not there. If it is not blocked, then the data is there. And you can go ahead to get the data, put it inside this variable, and then process the data. Okay? Now remember I mentioned to you that somehow, if let's say this is empty, right? So the producer comes in, it was empty, you put the data in there, right? So he has to signal to this consumer that the data is there. Okay, how does it signal? He has to do an up here. Empty, up. Take note that is empty, not full, right? It's empty. It does a full on the down. Sorry, it does a down on the full, but it does an up on the empty. Okay? So right now when it does an up, if this guy has been waiting for it because it's 0, initially it was 0, right? Okay, when it performs a down, it will be blocked. But the producer to produce something and put the data inside there, right now, it does an up to signal to this consumer there is data there. So it will wake up, that is unblock, and then proceed to take the data. Okay, now of course it will consume it also. So from 0 to 1, and back 1 back to 0, because it grabbed it. Alright? The same thing for this consumer. After he has processed the data, actually before he processes the data, I made a mistake. He has to do this one first, right? We should be doing this first. Full up, and then process data. Okay? So here it does a down, but because it grabbed one, right? It grabbed one. That means right now there is one empty slot there, extra slot. That's empty. So he has to tell the producer, you have one extra. So the full right now become it has one extra. Okay? So you do it down on the empty, you will do it up for the producer, so that the producer that is waiting there block because it's full maybe, has a chance to enter and then fill in the empty slot that has been taken away by the consumer. So the consumer take one, we got empty slot, and then it allow the producer to come in and fill in that space. Okay, so he has to do it up. So this is the thing that I was talking about, signaling. This one signal to the producer. This actually signal the consumer to unblock and then take the data. Whereas here is to signal to the producer that he has taken the data and we have empty slot, extra empty slot, so that the producer can come in and put the data in. Okay? So this is the signal. That's why you see this signal here. And there's a reason here, you see a weight. Why? Actually this is weight, this is signal. Okay? Another term for this is weight and signal. So let's see the terminology side by side. Okay, now hopefully have a better understanding.
So
this one is called full weight, the equivalent of it. Sorry. Okay. And this one is called empty signal. This one also same thing. This one is called full signal. Okay? So that's why we see here I use down, now I use weight, because like this kind of example, it's better to use weight and signal. Okay, weight meaning that if it's zero, then you weight. Same thing here. If empty is zero, then you weight. And who is going to unblock you? That means allow you to get past. Is the signal. So that means the producer will signal to the consumer, okay, you can go. Understand?
So the down both check the semaphore and the up both signal the
signal the other party that you can proceed on. Okay? Is that clear? Right? So that means if let's say the buffer is not full, why the buffer is not full? Because the consumer is consuming. So somehow you feel, the other side is removing, right? So that's why you have to signal. You indicate to the other party that, okay, I already removed, you have extra slot, suddenly you can put it. The same thing for the producer. When I have data inside there, if you are waiting, now I signal to you that you have one additional data. You can wake up and then take the data. Right? Once you take the data, you tell me that, okay, I can fill in the data. So they use two different semaphore. This semaphore is different ones. Okay, the producer will wait on the full, the consumer will wait on the empty, but it will never wait on the full. So semaphore is two separate semaphore. Okay. So that is basically how the process is done. Basically, it's just this. Okay? So this one is just synchronizing this buffer. But I haven't talked about the mutual exclusion yet. Okay? Mutual exclusion is another thing. Now, when I access into this buffer here, this buffer, remember I mentioned that if the data is shared, obviously this buffer is shared because the data is shared, right? And I can put in the data and then the other side can remove it. So somehow you will have race condition. Okay, somehow when I put the data halfway and then you remove and you can get into a race condition. You don't want that. Now in order to prevent this, you have to protect this buffer. Okay, how do you protect it? You protect it either with mutex or another semaphore, but this semaphore must be a binary semaphore. Okay? Now let's use the mutex, or maybe use binary semaphore also can. But let's use a simpler one. Let's call it mutex. Oh, sorry, I should be using a different color. Let's use green. So I got mutex. And let's call it mute. Okay? And here, when I do it, I will have to mute acquire. It's just the same like binary semaphore where you do a down. Okay? Once you finish, you do a mutex up or release. Okay, when you acquire, if it is not there, then it will get blocked. Okay? After, let's say, when you try to acquire, nobody is using it, then they can get passed, and then you can add the data inside. Once it's already finished with it, then you can release the mutex. The same thing here. This buffer is shared, right? Producer and consumer share this buffer, and somehow they can race with one another and can get this buffer to be in undeterministic state. So only one thread is allowed to meddle with this buffer. In order to allow only one thread to meddle with this buffer, we have to use either binary semaphore or mutex, because mutex only allow one person to use, right? So here also the same thing. Before I get the data, so I need to do mutex acquire and mutex release. Okay, I have only one mutex. I got two semaphore, but I got only one mutex. The semaphore full and empty is to synchronize the use of these buffer slots. Okay, and the mutex is to protect the buffer being accessed at the same time by multiple threads. Here we got two potential threads that is going to touch this buffer, which is shared, and we use this mutex to protect it. Meaning that if, let's say, the consumer able to enter into this critical region here, okay? So what you need to do is you have to acquire the mutex first, because producer might be inside this critical region as well. Okay? If both try to add and get, you might have race conditions. So you have to synchronize this as well. So meaning that before I allow anybody to touch the data inside there, I need to allow only one thread to enter, mutual exclusion. So I need to acquire the mutex first. Alright? So if, let's say, producer managed to acquire, but the consumer comes later, when he acquires, because it's already acquired there, try to acquire the second time, it will fail, right? Because producer managed to acquire, so you will get your wait or get blocked. And then the producer can enter and meddle with this buffer, you can add the data. Okay? And once it finishes, you will release it. Once it releases, now this guy who is waiting will be woken up or unblocked and then proceed to get the data. Once you get the data, you release. You can see that when you enter into here, only one thread can enter, even though the process is run concurrently. Meaning that they come at the same time, but this is going to synchronize the process by allowing one person to enter into this critical region and allow only one to meddle with it. Okay? So take note of the difference. The counting semaphore is to synchronize the use of the available resources, whereas the mutex or the binary semaphore is to protect the data that is being used from race conditions. These are two different things. Okay? Okay, so basically it's just that. If you look at the full code here, sorry, let's go to the full code there. The full code given in the slide is more complex than what I showed to you, because it uses another variable called count. Let's have a look. You see this count there? It uses a count. And it uses this count to count how many variables inside there. If, let's say, it is 0, that means there's nothing in there, and therefore I need to not do anything. If, let's say, if the count is more than 0, that means there is data for me to actually get it from for this consumer. The same thing for the producer. If the count is 0, that means I can add more. If the count is 8, that means I cannot add anymore because there's nothing inside there, right? Okay. And another thing is it uses this in and out. I use what did I use? I use a function call. So let's see how we implement this function here. Because I don't want you to get confused with what is shown there and my solution. Okay. So what you see inside there is this. So buffer. So buffer add. So I'm going to call buffer. I'm going to use a different color. Okay. So this is add, and here is the data. This is data. Okay. So this is the function of this buffer. Let's say it's void. Okay. And implementation inside there will be similar like what you see is buffer, buff, and here is in, and then in plus plus. Basically is data. Okay. Now the buffer is shared, the in is also shared. Okay? Because it might have producers, multiple producers. So if many producers come into here, we can have 8 producers inside this region here. And when it comes to this buffer, you must make sure that only one person matters to this buffer. So you have to acquire the text first, then add the data inside there. So make a mistake. Data should be something like this. Here should be data. Okay. So now my code is more or less the same like what you see here. Okay. I missed one more thing that I missed this buffer size. Okay, let's go and fix that. So here is plus and also buffer size. Goes to in plus 1 and then modulo with buffer size. Okay, why do you need to do modulo? Remember I mentioned to you that you can go beyond this, right? So modulo, you come back again. I mean, we use like this empty slot that's available there. So you need to modulo with the buffer size. The buffer size will be 8. So 0 to 7, if you go to 8, you go back to 0. Okay? That means you fill in here, and of course the consumer will consume it somehow from the beginning, right? So when this is empty, you come back and then replace it. Okay? So how about the receiver? The receiver also the same thing, buffer gap. So let's see how the buffer gap happens here. So buffer gap will be doing this. You consume the data, and then it does the same thing. Right? So we're going to do the same thing here. So here I have void. Sorry, here will not be void. Here will be data. Data. And buffer get. Okay, return data, and what you do here is data d buffer dot out. Okay, and then out equals to out plus 1 modulo with buffer size. Okay. Okay, I do not use the count. Actually, you can use the count, but I think that count is redundant. That's why you don't see me using count plus and count minus minus. Okay, so this buffer get is basically doing this. It get the data from this out and increment that out. So out is actually pointing to is an index number pointing to the element that is supposed to retrieve. Okay, in is the index number where the empty slot is so that we can put in the data. Right? Okay? So that is for the producer consumer. So let's recap. So what we have learned here, counting semaphore is to count how many resources that you have. You only allow that number of tracks to enter to utilize the resources available. And the full is indicating how many empty slots that's available to you. Okay, it means you got 8 empty slots. How about the empty semaphore? It's actually indicating how many elements of data that is inside the buffer. If it is 0, that means there's no data inside there, right? If it is 1, that means there's 1 data, right? And the consumer is going to wait on empty, right? Because if it is there's a data there, you will grab it, right? So if it is no data, then it's going to wait on that semaphore. The same thing for the producer. The producer will wait if there's no available free slot. That means the free slot has gone down to 0. Then they have to wait. If it is there's an empty slot, then it will start to fill in. And of course, it will get passed, and then it will fill in. And who is going to signal it is the other track that is going to signal. Okay? So the producer is going to wait on the full, and the consumer is going to signal the full. Okay? Similarly, the consumer is going to wait on the empty. Who is going to signal it is the producer is going to signal it. Because when the producer produces it, it has data, then you can unblock the consumer that's waiting on the empty run, so that it will proceed and then get the data. The same thing for the user. So that is how complete semaphore is used. But it's just to count the resources only. It does not eliminate the race condition. Now, in order to eliminate a race condition, we have to use another one. Either binary semaphore, which is also semaphore. The maximum value is 1. Initial value is 1. Okay? Maximum value is 1, initial value is 1. Right? Or mutex. Okay, mutex also the same thing. When you start, it will have a value of 1 as well. And the maximum value is also 1. Okay, so mutex as binary semaphore is kind of similar. So you can replace this with binary semaphore. So when you enter the time, if let's say you assume that this is a binary semaphore, maximum value is 1, initial value is 1. So when you acquire, it becomes 0. But it was 1 before, right? So you can have access and handle with the data, etc. Okay, let's say the consumer comes, and if this is binary semaphore, similar to binary semaphore, but it's already acquired by this producer, so it becomes 0, right? So when you try to acquire, it's 0, so you have to block. Okay, that means you have to wait. Okay? Wait on this binary semaphore. Now, when the producer finishes, you release it. That means if you do an up. When it does an up on the mutex, from 0 to 1, now it will unblock the track that is waiting here. Okay? And then you can proceed to do the job and then release it. Right? So you can see that whenever I enter into this critical region, this too is the critical region, which touch the buffer, which can cause race condition, they are protected by the mutex. Only one track can access. Now it can be something like this as well. Producer comes in, acquire, so it becomes 0. 2 consumer comes in at the same time. You try to acquire, both of them will get blocked. Right? Because right now it's 0, so both of them will get blocked. Now, when the producer finishes with it, he will release. But 2 is waiting, right? When you release, the mutex will become 1. The counter, it has a counter inside there as well. It will become 1. And they only allow or unblock one of the tracks that is blocking. Only one. Okay? That one is going to acquire it, and then go down to 0, and then proceed. The other one has to wait. Okay? Now, when it finishes, it releases it. Now, the other block, the consumer, is going to proceed to meddle with this buffer. So you can see that no matter how many tracks come in, only one track will enter. whether it's producer or consumer, only one track, right? So this will eliminate the race condition. Okay, so the counting semaphore is to count how many resources available, and you allow that many tracks to access to use the resources. And the binary semaphore and mutex is to prevent race condition if the data is shared and you have modify write operation on this shared data. Okay, so these are the elaboration of it. There's actually animation, but I cannot play it on here. I have to download it into Microsoft Slide, then I can play it. But you can try it at home. Okay? Now, another problem that is similar to the problem that I mentioned to you, this is actually a special case. Principal risk condition is basically just producer and consumer also. Except this time, the producer is more than one. Consumer is only one. Okay, you got multiple producer, you got only one consumer. So this is a special case. It's called principal because you got one printer who is consuming it, but you got many computers that is sending files for this computer to print. So you got multiple producer, a single consumer. But the problem is still the same. And you solve it using this same algorithm, no change. Exactly the same as algorithm. So this algorithm actually solves single producer, single consumer, or multiple producer, single consumer, or single producer, multiple consumer, or multiple producer, multiple consumer. You will solve that as well. So you don't have to come up with new algorithm in order to solve it. Okay, so critical section is the section of code that can cause a race condition. Okay, and in order to protect it, you have to use mutual exclusion, right? And there is only one process that can exist inside this critical section at a time. You cannot have two processes inside the critical section, only one. So critical section is a code section, okay, which matter with the shared data. Okay, and that shared data is read, modify, write kind of operation that you do. Okay, and of course, when you do this, use this new types of binary semaphore to protect it, you must make sure that you release it. If you don't release, then it's not bounded waiting time. Okay, bounded waiting time means you wait forever. So there's unbounded waiting time. Okay, so normally when you acquire, you have to release it, meaning that somehow at any given time, as the time progresses, you will somehow finish doing the job and then you will release it, right? Okay, another method to solve this, I showed you lock using spin lock. I also mentioned about mutex. I also mentioned about binary semaphore, right? And also mentioned about monitor. Monitor will come later. But there's another solution, which was suggested by this guy, Peterson. That's why the name is Peterson solution. It's also to solve the mutual exclusion problem. But this one does not require any special feature. It doesn't require special mechanism. Remember when we talked about mutex and binary semaphore, the operating system has to step in to check whether to block or unblock the track. Okay? If let's say the mutex is already acquired or the binary semaphore is 0, then you have to block the track, right? And how about when the mutex is not 0, let's say it's 1, then you allow it to proceed. There's no problem. Now that will require operating system to step in to block the tracks. But let's say if you don't have that kind of feature, or you don't have that kind of privilege to get the operating system to do it for you, you can actually program it yourself without the need of the operating system or any special mechanism. we use this Peterson solution. Now, one thing about Peterson's solution is that it can only handle 2 threads. Okay, you have more than 2 threads, then it cannot work. Okay, so it's a special case, only for 2 threads. You have 3 threads, then you cannot use the Peterson solution. You have to use another algorithm. But a lot of problems involve only 2 threads. Okay, that's why this solution is quite interesting, because it does not require operating system to step in to do all the blocking and unblocking. Because Peterson's solution do not require such thing if there's only 2 threads or two processes. And how does it do it? It just uses these 2 variables. Okay, the first variable is the turn. It's actually to tell whose turn is it. And the second one is a flag to indicate whether you're interested to enter into the critical region. Okay, and this flag is a Boolean flag, true or false. And the number here is 2. You can see here, why 2? Because 2 process. So the array here is always 2. Okay? Now the turn is indicating whose turn is it. The flag is indicating your desire to access into the critical region. Right? So here is the terminology used. Turn indicate whose turn. Flag is to indicate whether you want to enter into the critical region. Now the critical section, whether you're using Peterson algorithm, no-text, binary semaphore, is always the same. On entry, you have to acquire the mutex. Okay, after you successfully acquire the mutex, you perform the critical section. Okay, and then you exit the section by releasing the mutex of binary semaphore. Okay, and then the remainder of the section will be the code that is not critical. That means you're not sharing anything. Then you don't protect it. Now, the question is this: can I protect any section that is not critical? Yes, you can, but it's useless. Because when you acquire and you release, you use a lot of processing. You waste your processing power there. Okay? So don't protect any code that it does not need to protect. You only protect code that is critical. For example, read, modify, write kind of shared data. Okay? So don't simply use mutex in unnecessary places, because it can cause a lot of processing power that is being wasted. Right? Okay, let's have a look at the algorithm, the Peterson algorithm. So the Peterson algorithm is also the same thing. Just like what we have learned for the binary mutex and binary semaphore and mutex. Here, for mutex or binary semaphore, you do a down or you do acquire, right? And then you enter into the critical section, and then after that you release it. Okay? For Peterson algorithm, it's all the same thing. This is the way how you acquire. Okay, this is the critical section that is protected, and this is how you release it. Okay, and the code is very simple. There's only 3 lines and 1 line, and you're using that 2 variables, and there's nobody going to sleep here. Okay, no one go to sleep. Okay, so let's see how it works. First, when you come in, before you enter into the critical section, you have to express your desire to enter into this critical section. How do you express that? You express using the first line. You tell by using this flag. And this I is your ID, your thread ID. Let's say thread ID 0. Okay, 0. So you express that you want to enter into critical section by putting it to true. Okay? And next turn is who has the right to enter. Okay? Turn. Now the turn is not itself, which is I. It's actually the other person. Because there are only 2 threads, right? Either itself or the other thread. 2 threads, right? So it is being lenient. It tells the other thread, okay, I give you a chance to enter first. I tell using this flag that I have the desire to enter the critical section, but I give you a chance first. Okay? So I tell the other thread, you enter first. Okay? Even though the other thread do not intend to enter, it doesn't matter. but I give you a chance to enter by giving this the thread ID of the other thread equate to the turn. So I'm giving a chance to that thread to enter, and then I wait. There's while loop here. I wait. What do I wait? I wait by looking at the other thread's flag. Okay, because this J is the other thread is interested to enter into the critical region. Okay, and is it given the chance to enter? Okay, this one will be true because you set it to J, right? So this will be true. So let's look at this one. If the other thread is not interested, then this one will be false. And therefore, this whole thing will be false. And that means I can enter. Okay? Right? So I give the other thread a chance, but it doesn't show that it's interested. So this one will be false. And therefore, I will not wait and I will enter into the critical section. Understand? Now, once I'm done, because I'm done already, initially, before I enter, I show that I'm interested to enter, so I put it true. But once I'm done already, I show to indicate that I'm not interested anymore because I'm done with it. So I put it to false. Okay? Now, how does it protect it? Remember, I mentioned that I give a chance, I show my interest, and I give a chance. Now, let's say, for example, the other thread also try to enter the section, and it performing this as well, its own code, right? But that flag here is going to be flag J. The turn that is given a chance, if the turn equals to I, because it's giving this other thread a chance to enter. And the while loop here will be while flag I instead of J, and turn equals to J, then equals to I. So it's the reverse, the opposite. Okay? And then the critical section, and flag instead of I will be flag J equals to false. Okay? So let's see how it works. Initially when this thread comes in, it shows that it's interested, but if it is giving the other thread a chance. Okay? Now before you're able to do this, let's say this thread also executed. You also show that it's interested to enter. Okay? But before you're able to let I become its turn, before you execute that, then this guy managed to execute this one first. So right now you make it to true, right? So you see true, and this is also J. So you wait. Okay? And this thread that is coming in, what does it do? Okay, when you see the thread is true, but you see the turn is J, which is itself. That means you will get passed. And you enter into the critical region. And this guy is actually waiting. Okay? And then when it ends, the flag will be equals to, flag J is going to be equals to false, because it's done with it, right? So the guy who is waiting here just now was true, because it already existed, so flag J is going to be false. So when the guy here waiting and checking, we find out suddenly this one turned from true to false. So when it becomes false, it will also get into this critical region. So that's how this algorithm works. Okay, is by being friendly to the other thread by giving it a chance first, and this is how actually it prevents the race condition. Okay, if you are being greedy, this algorithm is trying to show to you. If you are trying to be greedy, you have race condition. But if you are friendly, you give others the chance first, you can prevent race condition. So you show your intent that you want to enter, but you give others a chance and you wait. Find the condition whether he is done using. If it is done using or he is not interested, then this will be false and you can enter. But if, let's say, he also showed the interest and you've already given him the chance, so you will wait. And the other guy will continue to proceed and execute. Okay, once it's done, you set its own flag, that is its own interest to false, and now it sees that, oh, it has no interest anymore, even though the turn is given to him. But right now he has no interest. That means I can use this code. That means I can execute this section. Okay? So that's how Peterson's solution works. Okay, this solution only works for 2 threads. If you have more than 2 threads, you cannot use this algorithm. You have to use the modified one. But the modified one is a bit more complex. I won't go into that. Okay, and it will not come out in the exam also. Okay, this is how actually it works. I mentioned to you, Bara, I should be using this diagram as now. You can see that here is I, here is J, this J, this I, this J is I, and this is I, this is J. Okay? And that is I, this is J. Right? And the critical section here is the same critical section or different critical section, depending on what you are protecting there. That means it depends on your program. Okay, so this is another solution apart from the usual lock that I mentioned to you. So this one is a specialized kind of lock, but it's seldom used if because it can only use for 2 threads or 2 processors. If you have more than that, then you cannot choose this algorithm. Of course, it's very simple. But one thing is not efficient. Why is it not efficient? Because it looks like a spin lock. When it fails this condition, when this condition is true, it's going to loop here for quite some time. So it's going to spin here for a while. Okay? So this one looks like a spin lock. Actually, it's not spin lock, but it has the properties similar like a spin lock. And it's easy to implement. And spin lock is a bit, actually spin lock is also quite simple, but it doesn't work this way. Okay, another way to prevent this mutual exclusion, to protect the critical section, that means you want to implement mutual exclusion, you can use this feature by disabling the interrupt. I believe all of you learned interrupt before, right? Have you learned interrupt in one of your studies? Have you learned interrupt? Maybe in assembly or something like that.
Yes.
You learned before, right? So this is the interrupt that is talking about here. What does the interrupt do? The CPU, when it runs, right? It runs a program. This is your CPU. And it's going to interpret the program. And which program that is interpreting is actually depending on the program counter. Is it correct? Instruction pointer or program counter. So the program counter is pointing at the next instruction that is supposed to execute. Okay? Now, because the CPU is a single core, it's going to execute only one program at a time. Right? Now, what does the interrupt do? The interrupt is normally come from external maybe. Maybe you have a device wanting to, let's say a printer, want data to be printed. So the CPU needs to stop what it is doing, okay? And then service the interrupt. So you go into the interrupt service routine, and the interrupt service routine will have code to actually load the data and pass the data to the printer. Let's say the printer is the one that generates the interrupt. Okay? That means the program counter will switch from here. Of course, you will save this last executed instruction somewhere in the stack most of the time. And then you switch this program counter to the interrupt service routine and service it. Okay? So once it services it, then you come back to here where it last execute and then continue. Right? So that's how interrupt works. Basically, you're interrupting the CPU to get the attention. When the CPU gives the attention, then the CPU can continue to execute the original program. Right? So how does the interrupt come into this our situation here? Now remember I mentioned to you that when you run the program, if you have a single core, here let's say you got only one core, but you have multiple tracks, track 0, track 1, track 2. Okay, and this is the timeline. The time progress downward. That means as the time goes, it will progress downward, right? Now, the one core here, you have to share among all these threads, right? So the core, first you will load this context and you execute a little bit. and then you touch switch. Okay, you touch switch to this track here, and this track is going to execute from here to here. Okay, and there's a time quanta there, how long? Maybe 10 microseconds. You give 10 microseconds to this track 1 to execute the code, and then you touch switch. Okay, you touch switch to track number 2 and allow track 1 to execute a little bit, maybe about 10 microseconds again, and then you touch switch again. Okay? Because you got one core, you have to share, right? So you share this core. And eventually, when you finish up to track, let's say you've got only 3 tracks running, and you go back to track number 1. So track number 0. Track number 0 will execute again a little bit. And then touch switch again, execute some more a little bit here, touch switch again, execute again a little bit here. And then this process will repeat. And each one of them, each small steps here, is going to be 10 microseconds. Touch switch, 10 microseconds. Touch switch, no. But if you do that very, very fast, it appears that this single core is executing all of them together at the same time, because it happens very quick. Right? Now, how does it touch switch? Interrupt. Okay? So the CPU actually can be interrupted by the timer. So the timer is determining how long the track is able to execute. So the timer will keep track. The timer will interrupt the CPU. So the CPU will say, oh, okay, time's up right now. So you touch switch. Right? And then you execute the next track. But when you execute, you reset the timer again. So the timer will start counting. Another 10 microseconds, you will generate another interrupt. And the CPU says, okay, right now time's up. You will switch to track number 2, and then you keep on doing that. Now, in order for the track to run concurrently, the timer is the one that keep on interrupting the CPU all the time and ask the CPU to switch. Okay? Now, what happens if I disable the interrupt? If I disable the interrupt, let's say the CPU is executing this, and I disable the interrupt.
It will not stop.
It will not stop, it will continue, right? So the rest will be starving. The rest will not have a chance to execute. Okay, so that is bad, all right? But actually, it's quite good also. Why? The problem that we all discussed just now, the race condition and all that. Why? Because all this thread is running at the same time. No. Let's say, for example, this guy is running, and it touched one of the shared variable. Okay, is read modify write, and it's reading it before it's able to write, and then touch switch. And this guy also read, but did not manage to write, and then touch switch again. When they come back here, now we have problems. Why? Because this guy who is not finished with the writing, right now able to write, and he overwrite the data that is done by the other track. So the multi-threading is the one that caused the problem. And to switch from one another, the CPU relies on the timer interrupt. And if you can temporarily disable the interrupt, that will be good. By temporarily disabling the interrupt, you don't allow the CPU to touch switch, and therefore you can prevent this race condition. Am I right? For example, if I know that I'm going to execute read modify right here. Okay? Now suppose the timer interrupts at this particular time, then I have problem because I did not complete this read modify right. I need to complete this read modify right in order to make sure that there's no race condition. What I can do is, before the timer expires, I disable the interrupt. So when I disable the interrupt does not come in. So the CPU will continue to run. Now when I finish my read modify write, that means I know that I read modify write, and therefore I complete the process. And if the CPU interrupt me later on, there's no problem because there's no race condition here because I finished my read modify write. So I can enable the interrupter. So I disable here, I put D, and I enable them, I put E, just after I finish my read modify write. So by the time when I enable, the interrupt will happen, allowing the CPU to be interrupted and task switch. Okay? So this guy also the same thing. Let's say it's doing the read modify write as well. Okay? It does the read and then modify and then write. You can disable the interrupt here and enable here. By doing that right now, you are sure that you complete this read modify write before the operating system is able to task switch, and therefore there will be no race condition, even though all of them are running in concurrently. Understand? Is that clear? The whole problem why we have race condition is because the read modify write is incomplete, and you task switch. Okay? If you are able to read modify write before you task switch, then race condition will never happen, even though there's a task switching that is happening. That means all these tasks is actually running concurrently using a single core. Okay, so that's the reason why it is here. The critical section problem actually can simply be solved by using the interrupt, disabling the interrupt. Okay, but if, of course you cannot disable too long. If you disable too long, now the operating system is not able to task switch, and therefore your program will look like not smooth. Or the program that is running will not run smoothly. Okay? So what you do is, before you read modify write, you disable the interrupt first. Normally we don't disable that, you disable before you read. Okay? Because all this need to be atomic. Okay? Atomic means it has to be executed before task switching happens. So you disable first, read modify write, enable. The same thing here. Before you do this read modify write on the shared data, you disable first, read modify write, enable. Okay? By doing that, then even though there's a task switching, there will never be a race condition at all. Okay? So disabling interrupt is one of the solutions, but this solution normally is not taken seriously, because in order to disable the interrupt, you need to have a special privilege. Only operating system has this privilege. Normally, ordinary code like this track has no privilege. Why? Anybody can figure out why the operating system has the privilege, but ordinary tracks cannot disable the interrupt? Simply disable the interrupt. Any reason? Okay, the reason is quite clear. Just now I mentioned to you. If the track is allowed or has the privilege to disable, it can disable forever. That means the operating system right now cannot task switch, and therefore it cannot do multitasking. Okay? If a virus comes in and do that, that means your program, only one program can run, the rest cannot run. Do you want that? You don't want that, right? So every of the track do not have the privilege to disable the interrupt. So disabling interrupt can be done only when, if your system is very simple. That means your operating system is relying on the credibility of your track. That means it trusts the track. If you can trust the track, then it can allow the interrupt to be disabled. But most of the time, operating systems don't allow you to disable the interrupt at all. Okay? Even temporarily. You need to have a privilege in order to disable the interrupt. Most of our program that is running do not have that privilege. Okay? So this is a special case. If let's say your program or your system is simple, where your program has the same privilege as your operating system, then you can use this kind of solution. But this solution is not the best solution. So the solution that is more probable is the mutex, binary semaphore, spin lock, and all that, because this solution do not require this kind of special privilege to disable and enable the interrupt. Okay? The reason why it prevents is because if you disable, you can mess up with the operating system. That's why the operating system don't allow you to do that. Okay? Another problem with this technique is if you're using multiprocessor, or multi-core may be okay, but multiprocessor, you have a core that is separated from one another. It cannot deal with it. Okay? Because when you disable the interrupt, you only disable the processor that you are using. It's not disabling the rest. Okay? Unless you have a way when you disable, it disable all the processors. Right? So this solution, one thing is you don't have privilege. That's the most, or the number one problem. Second, if you are multiprocessor, then when you disable the interrupt, you only disable one processor, but not all. Okay? Most of the time, you do not have this feature when you disable, it disable all the processors. Okay, so that is why you do not use the interrupt. Okay, just like what I showed you for the Peterson. Okay, before you enter the critical section, you have to acquire the lock first. The lock can be a spin lock, mutex, or binary semaphore. Once you have done using done with the critical section, then you have to release the lock. Okay, and here when you execute the remainder of the section, that is not critical at all. Okay, so that is how you use it. Now, I'm not going to talk about this atomic lock because it's more or less the same like what I mentioned to you last time, right? Except that this atomic lock is, most probably is talking about the spin lock. Okay, and when you lock, you have to lock at the same time, just like what I mentioned here. So this is atomic operation. Okay, and this is actually atomic lock using interrupt. Disable, this is atomic operation, and then enable. Okay. Okay, let's look at the semaphore. We are revisiting this. Okay, a binary semaphore looks like this. Let's say this is a semaphore, and put it semaphore. And let's put a SAM. Okay. And here initial value is 1. Sorry, maximum value is 1, initial value is 1. Okay, so this binary semaphore, the initial value start with 1. Okay, the maximum value is 1. Okay, so if I use this one looks like a mutex. Okay, it looks like a mutex that can mutually exclude one another. So if this is the critical section, okay, when I acquire, I do like this: SAM, down, wait, or acquire. So let's use acquire. Okay, I use this term acquire. Acquire means I get it. Okay, get the semaphore. Okay, I enter into a critical section, and then I do release. Okay, whoever comes in, try to acquire the semaphore, you will fail, you get blocked. Why? Because there's only one. If this track managed to acquire, it will reduce to 0, right? So any track that tries to acquire the same semaphore, okay, because it's 0, and it has to be blocked. Okay, the one that succeeded is the first track that managed to acquire. Then he has the chance to enter into the critical section and do the job. And when he releases, then the one that is waiting will be unblocked, and then he will acquire it and enter into his own critical section and then release it. So that is how this binary semaphore is used as a mutual exclusion protocol. Okay? To implement this mutual exclusion protocol. What is mutual exclusion? Mutual exclusion means the same understanding among all threads. If I access, you cannot access. Nobody can access except me. Only one can access. That is mutual exclusion protocol. It means that. Okay? And what can implement this? One of them is this binary semaphore with initial value of 1. Okay? Now let's look at another use of this binary semaphore. Another use of this binary semaphore is this way. Okay? Just now I mentioned to you is mutual exclusion. Now I want to talk about this. The max value is 1, but I start with 0. not 1, I start with 0. It's still binary semaphore. Why? Because the maximum is 1. That means it can be 1 or 0 only, right? Alright. The same thing as this. Maximum is 1. That means it's 1 or 0 or 1. So it's binary semaphore. This is also binary semaphore because maximum value is 1. It's either 0 or 1. But the initial value is 0. This initial value is 1. If initial value is 1, we use it as mutual, to implement mutual exclusion protocol. But if the initial value of this binary semaphore starts at 0, okay, when it starts with a 0, now this is not a mutual exclusion. It cannot implement mutual exclusion, but it implement another thing. It implement signaling. Okay, we use it as a signaling. Okay? If the binary semaphore starts with 1, we can use it as mutual exclusion protocol. But if the value starts from 0, we cannot use it for this. We actually use it for another purpose, called signaling protocol. Now, mutual exclusion is to allow only one track to enter so that it protects this critical section from race condition. That is the purpose of mutual exclusion. Now, let's look at this signaling protocol. What does it solve? It solves this. Let's say, for example, I have a track, and this track will not proceed until somebody signals. Okay? Let's say, for example, this data. Okay? I have a data here. It needs to be processed by track number 0 because track number 0 know how to process this. Okay? We want to process this data from one to another. Okay? Let's say, for example, this is the raw material, or the raw data. It needs to be processed, but only T0 know how to process it into another material or another form. Okay? And this data needs to be processed later on by another track. Maybe this track is executing specific instruction, the same thing as this. Or this is a different core, and it knows how to execute certain instruction, right? And then you transform this into another form of data. Okay? So somehow you can see that there's some kind of sequencing, right? First, before T1 able to get this data to transform it into another form, he has to wait for this T0 to complete its task. Right? That means T0 have to wait for T1. Is it correct? So in that case, how do we solve it? Let's say this is track 0, and this one is track 1. Right? Okay, let's say this is the data. Sorry, the data. I need to transform it into this form first. So here, my T0, what it does is this. I have to transform into this form first, right? Let's call this S1. Okay, S1. Right? I need to process it first. Process 1, let's say. And that is the data that I process. And I put it into this S1. Okay? Now, this S1 right now has the data, and it can be processed by T1. So T1 is going to process it, and I call it S2. So S2, I process again, but this is a different process 2, but this one is S1. Okay? Now, if I were to write like this, and I run this program concurrently, you see there's a problem there already. Why? Because when I process it, if this process haven't finished, and this guy start to process, but it process nothing, right? Because they haven't gotten the data yet, because it takes some time to process, right? And this might be empty. No, you cannot process it to get this S2, to get this, because you have to wait for T1 to complete the process. So how do you solve this problem? You use this binary semaphore, and you start with 0. And how do we do it? We do it this way. So instead of writing the code like this, I write it this way. For T0, I put S1, process, 1, the data. But for T1, I wait wait for this process to finish. And I use this semaphore to wait. I put semaphore, wait, down or acquire, okay? Depending on how you like it. Okay, so T1 is going to wait on this semaphore, okay? And then when this guy finish, you'll do like this, semaphore, signal. Okay, release or stop. Okay, and now I can process. S2 equals to process 2 S1. Okay, so this will cause problem. This will help the problem. Why? Imagine two tracks coming together at the same time, right? If let's say track 1 is faster, you wait on the semaphore, but look at the semaphore number, 0. 0 means it has to wait, because it starts with 0, not start with 1. Is that true? So you wait. Right? So T0 can go on and process it. It takes its own time. It can take 1 hour, it can take 2 hours, it doesn't matter. But once it's finished, it will signal the semaphore. It will signal, right now, 0 will become 1, and the operating system will unblock this T1 because it's 1. Okay? And then this T1 is going to acquire it. From 1, it becomes 0. Okay? And then you proceed to process. So right now, the sequence will be correct because it wait until S1 is completed, then only T1 will use it to process it. So you can see the signal happening this way. Right? So, binary semaphore, but initial value 1, it is used to implement mutex, which is actually it's not mutex, mutual exclusion protocol, to prevent race condition. But if it is start with 0, you cannot use it as mutual exclusion. It actually has a different application. It is used for signaling, and there's a signaling protocol. You can see here, it's signal, right? So when I finish, then I signal. T1, when it receives the signal, you continue to process. You take the data that is completed by S1. T0, which is S1. Is that clear? Okay, so that is the use of binary semaphore, and there are two types of binary semaphore. One binary semaphore is used for mutual exclusion protocol, implementing it. The other binary semaphore is used for signaling. It's not for that, but it's for this. So these two are two different usage, and they are different. Okay? Okay, here it does not show like what I showed to you. It shows to you S equal to 0, no off and all that, but basically it means the same. Okay, that is wait. Okay, if S is 0 or less, no operation, meaning that it will spin here, waiting for the signal to come. Okay, and then when the other side is ready, you will increment the counter. Okay, when you increment, the other side will stop waiting and then proceed. And of course, you have to decrement as well, right? Because when it get unblocked, it is 1, right? And before it able to proceed, you have to reduce it to 0. So 1 back to 0. So here, increase it to 1. Here, when you wait, when it get unblocked, you reduce back to 0. Okay, why it has to reduce back to 0 is to prevent the rest of the track that's coming in from into it. Okay, so only one that can access. Okay, so that is the use of the binary semaphore in two different kind of cases. Okay, this one is for mutual exclusion, and the other one is for signaling. Okay, this is an example of how it is used. Let's say process A, process B is two different processors that is run on ATM machine. Okay? Let's look at the code. I want to see whether there is any complete code there, no? Okay, there's no complete code, so let's imagine how it looks like. Okay? If we use binary semaphore as a mutual exclusion protocol to implement mutual exclusion protocol, then it should be something like this: semaphore. Let's call it SEM. And I start with 1 because it's mutual exclusion. You must start with. Sorry, the maximum is 1. You must start with 1. Okay. Let's say this is process A. Process A that is running on the first ATM machine. Okay. And before I do this, let's say somebody want to withdraw money. So this is ATM, teller machine. Right? What I need to do is I need to wait first. I need to wait on this semaphore. Wait. Okay? And then process it. So let's say somebody want to retrieve some money. So balance should be equals to or subtract with the amount. Okay, withdrawal. Okay, let's say withdrawal is the amount that is given by the user. Let's say you got 200 or maybe 1,000. You want to withdraw 200, just like the example there. So balance minus the withdrawal, the 200. Now you have to wait, right? If you don't wait, then you have problem. So here we try to protect this balance. This balance is the shared data, and we read, modify, and then you write. You read the balance, you modify by subtracting, and then you write. So this is read, modify, so you have to protect it. So here will be SEM signal. Okay, on the process B, which is running on another machine, maybe somebody is trying to retrieve the money as well. The same thing, semaphore wait. Okay, and you do the same thing, balance, withdraw, and then semaphore signal. Okay? Now, if you don't do this, what will happen? Let's say you don't have this. You don't have this. Okay, what can happen is this. Let's say, for example, you have a balance which is 1,000, right? And the withdrawal here by process is your father is actually retrieving, let's say the card is shared, your father is retrieving 200. So you read 1,000 minus 200. By right, it should be 800, right? But before you're able to write into the balance, let's say your mom is also using the same card, and then you try to retrieve at the same time, and the balance was 1,000 before, and you try to retrieve, let's say 800. Okay, 800. So you got 200 here, right? Now suppose you managed to write this 200 into the balance. Okay, read, modify, write. Okay, and this guy, your father actually retrieved the money as well as 200. But before he is able to write, your mom will write first. Get and write first. So you got only 200. And then when you write again, you overwrite the 200. Now you got 800. What do you remove? You withdraw 200 here. Your mom withdraw 800. You got 1,000. And then in your balance, you got 800. Not good, alright? Not good for the bank. Okay? So the bank have to implement this. Okay, so let's see how the bank perform this. So semaphore way. Your dad tried to access the ATM and withdraw 200, right? But before it minus the 200, you have to wait. But because it starts with 1, so it will enter. Now, because it enter right now, the binary semaphore becomes 0. Okay, your mom also use the ATM, another ATM, access it as well. But right now, because it's 0, okay, you will have to wait. Okay, you have to wait. Now your dad can proceed to do it. 200, and you get 100, and it will write into the balance. So right now your balance is 800. And then when it's signaled, then only your mom ATM machine can proceed. But right now the balance is correct, it's 800. So you take 100 minus 800, you get 0. And when you write into it, you get 0. So it's correct. Okay, so you can see that bank have to use this. If you don't use it, they lose a lot of money. Okay? Because otherwise, because of the risk condition, you become richer or you become poorer, depending on your luck. Right? And of course, with this protection, feature exclusion, this cannot happen. Okay? Okay, this one is basically explaining the consumer producer again, but I already explained to you. I will not explain anymore here. I want to talk about the last part. I think I have 15 minutes left, which is quite important. Yeah. Oh. One eight two. Sorry, 182. Sorry. 182. 966 182. Right. Okay, I use this last 15 minutes to explain the last part, and then we are done with this this lecture slide. Okay. I did mention to you, maybe in a practical, that you can make mistakes. And let's look at the mistake that you can do. Okay, suppose I have a binary semaphore or mutex. Actually, binary semaphore is the one that you can face problem. Semaphore, let's call it semaphore here. And I have something like this, 1, 1, okay? And I track 0, that is running like this. I wait on this semaphore. Okay? And then I do my critical section here. But when I finish my critical section, I did not release it. What can happen? I wait, that means I don't wait. I should say acquire better. I acquire.
Cannot use wrong.
Oh, sorry, I gave you the wrong one. Sorry. I gave you the previous class. It should be 615138. 615138. 615138. I'm sorry, because I was looking at the previous code. Okay, what is going to happen here, if let's say track 0, acquire the mutex, enter into the critical section, but did not release it. So 1 becomes 0, and it does not release it. What is going to happen? Okay, if let's say multiple thread that is going to execute the same code, what's going to happen is thread 0 successfully enter into the critical section, and there's no risk condition there. But the rest of the thread will be blocked forever. Okay, the rest of the thread will be blocked forever, and you will encounter this deadlock. Because you acquire and you never release. You are not the other track that is coming in is going to acquire it and they get blocked. And nobody is going to release it, so it's get blocked forever. No need one track after this. All the track that comes later, after track 0, they all is going to be blocked forever. So this is the first mistake that you can do. Meaning that if you use semaphore, the binary semaphore in the wrong way, you can get into this kind of situation. Deadlock means you cannot progress because you're blocking somebody else. Okay? So this is bad because the rest of the track that is acquiring it cannot progress at all, and there's no way for it to allow it to progress. In order to let it progress, you have to reset the program and rerun the program again. And of course, you have to change the code. Okay? Because if you run the code again, you'll get into the same situation. So this is the first number 1 problem. Issue number 1. Wrong usage of it, you acquire it, you forget to release. And you can cause the rest of the track to be blocked, except for T0. T0, when it acquires successfully, enter the critical section successfully, but you block the rest. Now, issue number 2. Let's say track 0, perform the semaphore, release. First, enter into critical section. And then semaphore acquire. What is going to happen here? This is problem number 2. Before you enter the critical section, it releases first. Initially it's 1, then when you release it, what? 0. No, you release the increment, even higher. Well, of course, the maximum value is 1, right? So you stay at 1. Right? You stay at 1. Now, other track that is also executing the same code, you will execute semaphore release, meaning that none is going to be waiting. Everybody is going to enter into this critical section at the same time. You will have race condition. Okay? This one, block all other tracks forever. I mean, all other track that is acquiring the mutants, not all other track, but all other track that is acquiring these mutants will be blocked forever. If you use it this way, you will enter into this kind of condition, race condition, where actually this critical section is never protected at all because you release first. You're supposed to acquire, not release. Okay? So this is the second problem. Okay, how about the third problem? I'm showing you this problem because if you are a beginner, normally you make this kind of silly mistake. Okay? So you need to know what kind of mistake that you do. Right? So issue number 3 is you acquire. You go into the critical section, and then you acquire again. Yeah, you do it correct. You enter into the critical section, no problem. But you acquire the second time. What's going to happen? Instead of releasing, you acquire the second time. What's going to happen? Okay, all concurrent track that is running this critical section, so all of them will encounter this race condition. How about this one? I got 6 minutes. I tried to finish all of them. I got, I think, 5 or 6 different scenarios. So what is the problem here? Acquire, enter into critical section, acquire the second time. The first one is correct. This one is also correct. You only allow one to access. So up to this point is correct. But after that, T0 acquire.
Same as 1?
Yeah, almost the same as 1, but this time, T0 itself will be deadlocked. So this one is called self-deadlock. Self-deadlock because when you acquire, it becomes 0, right? And then you acquire the second time, you get blocked because it's 0. The first time when you acquire from 1 to become 0, and now it's 0, you acquire the second time, you'll be blocked. So this is called self-deadlock. And self-deadlock will lead to blocking others as well, and blocking others. Blocking other concurrent track forever as well. Okay? So these are the third one. Okay, actually the fourth one will be release, critical section release. It can be a silly mistake as well, right? First is the mistake, and then you release it the second time. Double mistake. Okay, the problem will be the same, race condition for all concurrent threads. Okay? Now how about so acquire, release.
那个是我的是 surf deck 啊。
Okay, how about this one?
你们如果要 allowance 看我必要来啦，那 allowance 就是很高。在哪里有你的？在
third one. T0 semaphore acquire. Sorry, release, but then does not release after that. Critical section. And do not do anything else. Okay, this problem is the same problem as the second one. You release, okay, which is wrong already, and you enter the section, and then you don't do anything here. Okay, so this one is release, acquire, but this one is release, and then don't do anything. So what is going to happen? Okay, it's the same problem as this. So it's race condition for all concurrent threads. Okay, so that is the mistake that you can do. So this is number 4. Okay, so it's 1, 2, 3, and then 4. Okay? Okay? And number 5. This is the last one. Let's say this thread 0, and it's going to do this. It's going to do critical section first, and then only release. What's going to happen here? It does the critical section, then it release. First thing is it did not acquire, and you enter into critical section. So you have race condition. Okay? And when you release, if the maximum value is 1, right? So it's already 1, you release it to 1 still. Right? So it will be 1 forever. Meaning that here it will be race condition for all concurrent threads as well. Race condition for all concurrent threads. Okay, it looks kind of, if you look at it, how come this guy is so silly? And it happens to everybody. Yeah? Sometimes when you look at your code is very messy, a lot of code inside there, you will make this one mistake. You acquire, you forget to release. Or if you read the code and you forgot, and you interchange this, sometimes you make mistake, right? You release first, then you acquire. It's a silly mistake, but it's potentially a problem. Or you acquire, and here you mistype. Instead of putting release, you acquire. Okay? Or this one, instead of acquiring, you release, and then you don't do anything. Or here, you forget to acquire, but you remember to release. Also problem. Okay? Now, how do you overcome this? Of course, I cannot tell you. Yeah, you have to be careful. Of course, everybody is careful, right? And most of the time, you make mistakes, right? So that's why the programmer, the operating system designer, they say, okay, I provide you semaphore, but I know that you're going to make mistake. I give you this, but I'm going to give you another kind of lock, which you will not make this mistake. And I'll cover this next week. Okay? I don't have enough time. I'll cover next week. Get this other lock. You don't make this kind of mistake. Okay, you can leave now. I think yes. You can leave now. I think the student outside.